Implementation of AI-enhanced memory systems in 2024. Overview. In 2024, the educational technology landscape is set to undergo a significant transformation with the implementation of AI-enhanced memory systems leveraging insights from neuroscience. With a projected budget of $3.2 million, this initiative aims to enhance learning outcomes by improving memory retention and cognitive support for students. The project will unfold in 4 key phases, each designed to ensure a comprehensive and effective integration of AI tools in educational environments. Phase breakdown. 1. Research and development (R&D). The first phase is dedicated to extensive research and development focusing on data collection and the formulation of AI models that draw from contemporary neuroscience research. This phase involves collaboration with cognitive scientists, educators, and tech developers to identify the key memory mechanisms that can be effectively harnessed through technology. Key activities during this phase include partnership formation. Establish partnerships with universities and research institutions specializing in neuroscience and cognitive psychology to ensure that the AI models are grounded in scientific evidence. Data collection. Gather data on existing memory theories such as the spacing effect, retrieval practice, and dual coding to inform the design of the AI tools. Model development. Create AI algorithms that simulate neural pathways, optimizing them for educational use and tailoring them to meet the diverse needs of learners. Timeline. This phase is expected to kick off in Q1 2024, with initial research and partnership agreements established. 2. Prototyping and testing. The second phase involves the development of prototypes based on the insights gained from the R&D phase. These prototypes will be AI-enhanced memory tools designed to improve information retention among students. Key activities include prototype creation. Develop initial versions of the AI tools, which may include applications or software that utilize machine learning to adapt to individual learning styles. Pilot programs. Implement pilot testing within selected classrooms where educators will use these tools to gather real-time feedback on their effectiveness. Data analysis. Analyze data collected during the pilot programs to identify strengths, weaknesses, and areas for improvement. Timeline. The prototyping and testing phase is scheduled for Q2 and Q3 2024, with pilot testing commencing in the latter part of Q3. 3. Implementation and training. Following successful testing, the third phase focuses on the broader implementation of AI memory systems across various educational settings. This phase also emphasizes the importance of training educators to ensure effective integration of these tools into their teaching practices. Key activities include widespread rollout. Begin the rollout of AI memory tools in multiple educational institutions, including elementary schools, high schools, and universities. Educator training. Conduct training workshops for teachers focusing on how to integrate AI tools into their curricula effectively. This will include practical demonstrations and resources for ongoing support. Feedback mechanism. Establish a system for continuous feedback from educators to refine the tools and training materials. Timeline. Implementation will start in Q4 2024, coinciding with the completion of educator training workshops. 4. Evaluation and scaling. The final phase will involve a thorough evaluation of the impact that AI-enhanced memory systems have on student learning outcomes. This will help determine the effectiveness of the initiative and guide future scaling efforts. Key activities include impact assessment. Collect and analyze metrics related to memory retention and academic performance. This will include standardized test scores, student engagement levels, and qualitative feedback from educators and students. Iterative improvements. Make necessary adjustments to the AI tools based on evaluation data to enhance their effectiveness and usability. Scaling strategy. Develop a strategy for scaling successful programs to a broader array of educational contexts, ensuring that diverse populations benefit from the innovations. Timeline: the evaluation phase will commence in Q1 2025 with adjustments made based on collected metrics and feedback. Common themes and differences. Across various sources discussing AI-enhanced memory systems, several common themes emerge. Collaboration: there is a strong emphasis on the necessity of collaborative development involving educators and neuroscientists to ensure the tools are relevant and effective. Data-driven decision-making: the importance of using data to inform design choices and evaluate the impact of the AI tools is consistently highlighted. However, differences in projected timelines for the phases exist. Some sources advocate for a more aggressive rollout strategy emphasizing rapid deployment and iteration, while others recommend a cautious approach stressing the need for thorough testing and evaluation before widespread implementation. Conclusion: the implementation of AI-enhanced memory systems in 2024 represents a significant endeavor to bridge the gap between neuroscience and educational practices. With a dedicated budget of $3.2 million, the project aims to transform learning experiences by enhancing memory retention and cognitive support for students. As it unfolds through the planned phases of research, prototyping, implementation, and evaluation, the project will strive to ensure that technological advancements serve to enrich educational outcomes, ultimately fostering a more effective learning environment for all students. Timeline of events: Q1 2024, initiation of the R&D phase, partnerships established. Q2 2024, completion of initial research and development of prototypes. Q3 2024, pilot testing of AI memory tools in selected classrooms. Q4 2024, start of the implementation phase and educator training workshops. Q1 2025, comprehensive evaluation of pilot programs and adjustments based on feedback. As this project progresses, ongoing monitoring and adaptation will be crucial to maximize the benefits of AI integration in education, ensuring that students receive the cognitive support they need to succeed. The implementation of AI-enhanced memory systems in education in 2024 represents a significant shift in how technology and neuroscience can be integrated into learning environments. The project, with a budget of $3.2 million, is structured into 4 key phases: research and development, prototyping and testing, implementation and training, and evaluation and scaling. Each phase is designed to leverage insights from neuroscience to improve memory retention and cognitive support for students. Counterintuitive information. 1. The role of neuroscience in education. While many believe that educational technology primarily relies on data analytics and adaptive learning algorithms, the integration of neuroscience insights may seem counterintuitive. It suggests that understanding the biological basis of memory and learning is just as critical, if not more so, than solely relying on technological advancements. This approach indicates that successful educational technology must be grounded in a deep understanding of cognitive processes, challenging the notion that tech can operate independently of educational psychology. 2. Teachers as facilitators, not replacers. The common perception may be that AI tools will replace traditional teaching methods, thereby diminishing the role of educators. However, the focus in the implementation phase emphasizes that technology will serve as a complement to traditional methods. This counterintuitive stance highlights the importance of human interaction in learning processes, suggesting that technology should enhance rather than supplant the educator's role in the classroom. 3. Iterative improvement through real-world feedback. The reliance on pilot programs and real-world classroom testing may seem to contradict the typical tech development approach, which often prioritizes extensive in-house testing before public release. The decision to gather data from actual classroom environments indicates a belief that practical feedback is more valuable than theoretical models, which is a departure from traditional tech rollout strategies. 4. Cautious versus aggressive rollout. There are differing opinions on the timeline for implementation, with some advocating for a cautious approach that prioritizes thorough testing over aggressive deployment. This divergence challenges the common assumption that faster implementation leads to better outcomes. The emphasis on careful evaluation suggests that rushing to integrate new technology without adequate testing could be detrimental to educational effectiveness. 5. Budget allocation and resource management. The projected budget of $3.2 million may seem modest for such an ambitious initiative. Many technological endeavors receive significantly larger funding. This counterintuitive perspective implies that effective educational tools do not necessarily require vast financial resources but rather intelligent allocation of existing resources combined with strategic partnerships with educators and neuroscience experts. 6. Focus on memory retention over information delivery. Typically, educational technologies emphasize efficient information delivery such as through gamification or multimedia content. However, the focus on enhancing memory retention through neuroscience may seem counterintuitive, as it shifts the emphasis from simply transmitting knowledge to ensuring that knowledge is retained and utilized effectively. This suggests a fundamental rethinking of educational priorities, from simply delivering content to enhancing the cognitive processes that allow for long-term learning. 7. Emphasis on data-driven decision-making. While data-driven approaches are commonly accepted in educational technology, the emphasis on continuous evaluation and adaptation in this initiative points to a nuanced understanding of data's role. Rather than merely using data to assess performance after implementation, the project showcases a commitment to iterative improvements based on real-time feedback, which challenges the traditional practices of static assessment post-launch. 8. Scalability based on success metrics. The plan to scale successful programs based on specific metrics may seem counterintuitive, as many educational initiatives focus on broad implementation regardless of localized success. This approach indicates a shift towards a more tailored, evidence-based model for educational technology deployment, where the scalability of programs is contingent upon demonstrable success rather than a blanket rollout. Conclusion. The integration of AI-enhanced memory systems into educational technology in 2024 is set to challenge existing paradigms in both education and technology. By focusing on neuroscience, emphasizing the role of educators, and adopting a cautious yet iterative approach to implementation, this initiative underscores a transformation in how we perceive the interplay between technology and learning. The counterintuitive insights presented highlight the complexity and potential of this endeavor, promising a more nuanced understanding of educational effectiveness in the digital age. In the report on the implementation of AI-enhanced memory systems in 2024, several crucial pieces of content are easily overlooked, yet they hold significant implications for the success and effectiveness of this initiative. Below are key aspects that deserve deeper attention, along with explanations of their significance. 1. Collaboration with cognitive scientists. While the report mentions collaboration with cognitive scientists during the research and development R&D phase, the depth and nature of these collaborations are critical to the project's success. This partnership is not merely a formality, it is essential for translating complex neuroscience findings into actionable educational strategies. Cognitive scientists can provide insights into memory mechanisms such as working memory capacity, long-term retention strategies, and the neurobiological basis of learning. Significance: effective communication between educators and cognitive scientists can bridge the gap between theory and practice. If the AI models developed do not accurately reflect how students learn and retain information, the resulting tools may not be effective. This collaboration should be ongoing rather than just a preliminary phase, ensuring that as new research emerges, the AI systems can be updated accordingly. 2. Iterative testing and feedback loops. The report briefly touches on pilot programs in the prototyping and testing phase but does not emphasize the importance of iterative testing and feedback loops. Continuous feedback from both students and educators during these trials is crucial for refining the AI tools. An iterative process allows for adjustments based on real-world classroom dynamics, which can significantly differ from controlled testing environments. Significance: this feedback mechanism is vital for creating tools that meet the actual needs of students. If the testing phases are rushed or feedback is not adequately integrated, the final product may fail to address key challenges in memory retention and learning engagement. Emphasizing a robust feedback loop can lead to a more responsive and effective tool. 3. Educator training and integration. The report mentions the implementation phase, which includes training for educators. Yet it does not delve into how this training will be structured or the specific skills teachers will need to effectively integrate AI tools into their curriculum. The success of AI-enhanced memory systems hinges on the ability of teachers to adopt these tools in a way that complements their existing teaching practices. Significance: without comprehensive training, there is a risk that educators may either underutilize the technology or misuse it, leading to minimal improvements in learning outcomes. Training should not only focus on how to use the technology but also on understanding the underlying neuroscience principles that drive the tools. This knowledge can empower teachers to make informed decisions about when and how to deploy AI-enhanced memory systems in their classrooms. 4. Evaluation metrics and scalability. The report outlines a plan for evaluating the impact of AI systems on learning outcomes but lacks specificity regarding the metrics that will be used. Understanding how success will be measured is critical for assessing the effectiveness of the initiative. Metrics might include not just academic performance but also student engagement, retention rates, and even emotional responses to learning activities. Significance: clear quantifiable metrics are essential for determining the success of the AI-enhanced memory systems. A lack of rigorous evaluation could lead to the continuation of ineffective practices. Furthermore, the scalability of successful programs relies heavily on documented outcomes, without solid data justifying the expansion of these systems into broader educational contexts may prove difficult. 5. Long-term commitment and funding sustainability. The report states a projected budget of $3.2 million, yet it does not address how long-term funding will be secured to support ongoing development, maintenance, and enhancement of the AI systems. Educational technology initiatives often face sustainability challenges once initial funding runs out. Significance: a one-time investment may not be sufficient to ensure the longevity and continuous improvement of the AI-enhanced memory systems. Planning for future funding sources, such as grants, partnerships, or revenue models, will be crucial for maintaining momentum and adapting to new educational challenges as they arise. 6. Ethical considerations and data privacy. While the report focuses on the technical and educational aspects of the implementation, it overlooks the ethical implications of using AI in education, particularly concerning data privacy. As AI systems collect and analyze data on student performance, there are significant concerns about how this data is stored, used, and protected. Significance: ethical considerations are paramount in maintaining trust between educational institutions, students, and their families. A failure to address data privacy issues can lead to backlash from parents and educators, potentially jeopardizing the entire initiative. Developing a clear ethical framework and privacy policy will be essential for the successful rollout and acceptance of AI-enhanced memory tools. 7. Diverse learning needs and accessibility. The report does not explicitly mention how AI-enhanced memory systems will accommodate diverse learning needs, including those of students with disabilities or varying cognitive abilities. Tailoring educational technology to be inclusive is vital in ensuring equitable access to learning resources. Significance: if the AI tools do not consider diverse learning styles and needs, they risk alienating a portion of the student population. Incorporating accessibility features and ensuring that the tools can adapt to various learning requirements will enhance their effectiveness and promote a more inclusive educational environment. Conclusion: the implementation of AI-enhanced memory systems in education presents a significant opportunity to leverage neuroscience for improved learning outcomes. However, the successful realization of this potential hinges on addressing often overlooked aspects such as collaboration with cognitive scientists, robust testing and feedback mechanisms, comprehensive educator training, clear evaluation metrics, long-term funding strategies, ethical data use, and inclusivity. By focusing on these areas, stakeholders can better ensure that the project not only meets its initial goals but also creates lasting positive impacts on the educational landscape. Here are the 4 most valuable points to focus on for an in-depth analysis and discussion regarding the implementation of AI-enhanced memory systems in educational technology in 2024. 1. Integration of neuroscience insights into AI systems. Analysis. The foundation of this initiative lies in the collaboration between AI developers and cognitive scientists. This integration is crucial as it ensures that the AI tools are built on scientifically validated principles of memory and learning. Understanding cognitive processes such as encoding, storage, and retrieval of information will lead to more effective educational tools that align with how the human brain functions. This point raises questions about the depth of neuroscience research being utilized and the potential for ongoing research to adapt these tools as our understanding of cognition evolves. Discussion. What specific neuroscience findings will guide the development of these AI systems? How can educators be involved in the R&D phase to ensure that the tools developed are practical and directly applicable in real classroom settings? 2. Prototyping and iterative testing. Analysis. The second phase emphasizes prototyping and iterative testing, which is vital for refining the AI tools based on real-world classroom experiences. This stage allows for adjustments based on feedback from educators and students. Fostering a user-centered design process. Pilot programs will be essential in identifying any shortcomings or unexpected effects of the technology on student engagement and learning outcomes. Discussion. How will the success of these prototypes be measured? What are the specific metrics that will indicate improvements in memory retention and academic performance? Furthermore, how will pilot programs ensure a diverse range of educational environments to test the tools effectively? 3. Implementation and educator training. Analysis. The rollout of AI-enhanced memory systems must be accompanied by comprehensive training for educators. This ensures that teachers are equipped not only to use the technology but also to integrate it into their teaching methodologies effectively. This training is pivotal for addressing any resistance from educators who may be skeptical about new technologies or who may feel overwhelmed by the integration process. Discussion. What strategies will be employed to facilitate educator buy-in and smooth implementation? How can ongoing support and professional development be structured to help teachers adapt to integrating AI tools into their classrooms? 4. Evaluation and scaling. Analysis. The final phase focuses on evaluating the impact of AI systems on educational outcomes and scaling successful programs for broader implementation. This phase is critical in determining the efficacy of the AI tools and justifying the $3.2 million budget. The evaluation process must be rigorous, utilizing both qualitative and quantitative data to assess the real-world impact on learning. Discussion. What specific evaluation frameworks will be used to assess the effectiveness of the AI-enhanced memory systems? How will findings inform future iterations of the technology? Additionally, what criteria will determine which programs are scaled and how can success be shared across different educational contexts to maximize impact? These 4 points provide a comprehensive framework for analyzing the potential impact of AI-enhanced memory systems on educational technology, highlighting the importance of research, testing, training, and evaluation in achieving successful integration and improved learning outcomes. 1. The Human Genome Project 1990 to 2003. This was an international scientific research project aimed at mapping and understanding all the genes of the human species. The project had a budget of around $3 billion and involved multiple phases including planning, data generation, and analysis. Like the AI-enhanced memory systems initiative. The Human Genome Project required collaboration between various experts including geneticists, bioinformaticians, and researchers from numerous institutions. The project's completion has had profound implications for numerous fields including medicine, genetics, and biotechnology, similar to how AI-enhanced memory systems aim to transform educational technology. 2. Project Apollo 1961–1972. NASA's Apollo program was a series of missions aimed at landing humans on the Moon and bringing them safely back to Earth. The initiative involved extensive research, development, and testing phases with a budget that eventually exceeded $25 billion. The program required collaboration between engineers, scientists, and astronauts to develop the necessary technology and training for successful missions. The structured phases of Apollo, from initial concept and design to implementation and evaluation, mirror the planned phases in the AI-enhanced memory systems project, underscoring the importance of comprehensive planning and testing in achieving groundbreaking results. 3. The Manhattan Project 1942–1946. This was a research and development project during World War II that produced the first nuclear weapons. With a budget of approximately $2 billion, equivalent to around $30 billion today, it involved multiple phases including research, development, testing, and deployment. Collaboration among scientists, engineers, and military personnel was crucial, similar to the interdisciplinary approach of integrating neuroscience into educational technology. The Manhattan Project has had lasting impacts on science, military strategy, and international relations, akin to the potential long-term effects of AI-enhanced memory systems on education and cognitive development. The implementation of AI-enhanced memory systems in educational technology is set to unfold across 2024 and into 2025. Driven by a projected budget of $3.2 million. This initiative is structured around 4 key phases that leverage insights from neuroscience to enhance student learning outcomes through improved memory retention and cognitive support. Here's a detailed future outlook based on the proposed phases and broader trends. Future outlook for AI-enhanced memory systems. 1. Transformation in learning methodologies. As the integration of AI-enhanced memory systems progresses, we can expect a significant transformation in pedagogical approaches. The first phase of R&D will lay the groundwork by merging neuroscience with educational practices. This synergy is likely to lead to personalized learning experiences tailored to individual cognitive profiles. By 2025, educators will increasingly adopt these methodologies, moving away from one-size-fits-all teaching to more customized learning paths that cater to the unique memory capabilities of each student. 2. Enhanced engagement through interactivity. The prototyping and testing phase will focus on creating tools that engage learners interactively. AI systems that mimic neural pathways are expected to facilitate dynamic learning experiences. By 2025, we may see classrooms equipped with interactive AI systems that respond in real time to student inputs, offering tailored feedback and adaptive learning resources. This could lead to higher student engagement levels as learners find themselves more actively involved in their educational journeys. 3. Comprehensive educator training. As implementation progresses, the importance of educator training will become paramount. The third phase emphasizes equipping teachers with the knowledge and skills needed to integrate AI tools effectively into their classrooms. By 2025, a robust framework for ongoing professional development will likely emerge, enabling educators to adapt to technological advancements and leverage AI tools to enhance traditional teaching methods. This professionalization of educational technology use will foster a culture of innovation in teaching practices. 4. Data-driven decision-making. The evaluation and scaling phase will emphasize the collection and analysis of data to measure the impact of AI-enhanced memory systems on learning outcomes. As schools and educational institutions begin to implement these tools, there will be a growing reliance on data to inform teaching strategies and curriculum development. By 2025, expect educational institutions to adopt a more data-driven approach utilizing metrics from AI systems to continually refine curricula and teaching methodologies based on student performance and engagement levels. Broader implications and trends. Ethical considerations and data privacy. As AI systems become integrated into education, ethical considerations surrounding data privacy and security will gain prominence. Stakeholders will need to establish clear guidelines to protect student information while harnessing the potential of AI. By 2025, policymakers may introduce regulations that govern the ethical use of AI in education, ensuring that student data is handled responsibly. A collaboration across disciplines. The success of AI-enhanced memory systems will depend on ongoing collaboration between educators, neuroscientists, and technologists. This interdisciplinary approach is likely to foster innovation, leading to the development of more effective educational tools. By 2025, collaborative networks may emerge, providing a platform for sharing best practices and research findings that enhance the effectiveness of AI in educational contexts. Global accessibility and equity. As AI-enhanced memory systems prove their efficacy, efforts will be made to ensure these innovations are accessible to a broader range of educational settings, including under-resourced schools. By 2025, initiatives aimed at equity in education may focus on providing access to AI tools for disadvantaged communities, potentially narrowing the educational achievement gap. Shift in assessment practices. The introduction of AI systems will likely revolutionize assessment practices within education. Traditional testing methods may evolve to incorporate AI-driven assessments that provide a more comprehensive understanding of student learning and memory retention. By 2025, we may see the emergence of formative assessments that continuously adapt to student needs, providing real-time insights into learning progress. Conclusion. The future outlook for AI-enhanced memory systems in education is promising, with the potential to fundamentally reshape teaching and learning practices by 2025. As these systems are developed and implemented, they are expected to foster personalized learning experiences, enhance student engagement, and promote data-driven decision-making in education. However, careful consideration of ethical implications, collaborative efforts across disciplines, and a focus on equity will be essential to maximize the benefits of these advancements. The projected investment of $3.2 million reflects a commitment to harnessing technology for transformative educational outcomes, paving the way for a new era in learning.